Hey everyone, hope you're doing well. This week we're going to pivot to species interaction models. So as you probably have realized by now, population viability analysis, which is what your final projects are all about, are pretty single species focused largely. But species are nested within a much more complex ecosystem, and where models really start to get interesting is where we start to try to model interspecies interactions like competition and predation. All right. Now, you've probably learned something about species interactions in ecology classes in the past. And before we get started with trying to model competition, which is the first of the processes that we're going to go through, we'll do predation next week. But before we really get into that, just as a review, what I'd like you to do is to just try to refresh your memory about different types of species interactions that are possible in real world systems. So there's, interactions can be positive and can be negative, right? So predation is positive for the predator and negative for the prey, right? Competition, we can imagine, might be negative for both, but there are several other types of interactions. An interaction can be positive for both species in a two-species interaction. An interaction can be positive for one species and kind of neutral for another. An interaction can be negative for one species and neutral for the other. So there's a bunch of different types of classifications of species interactions. And I know we're not going to go much further than this, but just as a review, please pause the video, go into Top Hat and answer the first question, and then resume the video. All right. Today we're going to talk about competition. Actually, the next two lecture periods, or however you choose to complete these lectures, we'll be talking about competition. Competition is a type of interspecies interaction where the vital rates of each species is negatively or are negatively influenced by the presence of the other. So this is a negative interaction. So hopefully in your Top Hat question, you correctly answered that this interaction where both species are negatively impacted, that's competition. So one really important point is that there's not much difference within species competition, which is one of the primary mechanisms that we've talked about for density-dependent population regulation, where there's so many species of your or individuals of your own species that you're competing with them for resources. That's that's intraspecies or within species competition, and then interspecies competition is competition among species for resources. But the mechanism's kind of the same. The two main mechanisms underlying competition among species or within species are exploitation competition and interference competition. Exploitation is often what we think about first, where all individuals are competing for resources and all have maybe similar competitive abilities. There's a limited pie and it's first come, first serve. This is often called scramble competition, especially when it's referring to intraspecies competition. But really just think about it as competition for resources, exploitation competition. The other is called interference competition, and this can happen within species, but often happens among species. This is where the negative effect of one, and I say actor here, but just an individual of either the same or another species on another actor in an ecological system is due to direct behavioral exclusion. All right? So interference competition is where one individual excludes the other. So there may be a limited pie, but it's not first come, first serve. It's not a scramble competition. It is one individual takes the whole pie and one individual gets nothing because one individual is stronger or it's able to keep that other individual off the resource entirely. Birds do this by maintaining territories. A lot of species are able to maintain territories and they keep individuals of their own species off their territory, but they also keep any potential competitors away as well. Some plants engage in among species interference competition. Here is a black walnut tree, which is famous for its allelopathy, which means that it excludes, using chemical mechanisms, it excludes the growth of other plants nearby. So it basically takes over the resources, using, in a sense, a behavioral mechanism to interfere with the growth or vital rates of other species around it. So that's allelopathy, so that interference competition can happen both in plants and animals. All right, so that's kind of the really, in a broad way, that's the mechanisms behind competition within or among species. Let's talk a little bit about modeling competition. Now, if we've said that intraspecies competition and interspecies, or within and among species competition, are essentially the same process, maybe we can model these processes in the same way, and we can think about the logistic growth equation, which we have memorized basically at this point. The change in the abundance is equal to R intrinsic, or R max, intrinsic rate of population growth, times N, which is just basic exponential growth, and then mitigated by this 1 minus N over K term, or the degree to which carrying capacity is empty. So as carrying capacity gets full, this growth term goes down to 0. So that's the basic logistic growth equation. That's for one species, a single species model. We've gone over this model. Now let's look at a case where we have two species whose dynamics are described by logistic growth, basic logistic growth. So this is just the same equation as up here, but now with two different species. So we have species 1 and species 2, both growing with a logistic growth model where they have carrying capacities that may be different, K1 and K2, and the growth rate could be different too. So we could subset this R1 and R2, but basically we have two different logistically growing populations. Now we can imagine that the population growth for each species may be further depressed by the presence of the other, and this is where we start to get into competition. So we can imagine a scenario where species 2 actually can use some of the resources for species 1 and basically fill up some of its the carrying capacity for species 1. So if there's some individuals of species 2 in the area, the area can't support as many individuals of species 1 because species 2 individuals are using up the same resources, and vice versa. If species 1's around, it's going to use up some of the resources for species 2, and therefore the landscape cannot support as many individuals of species 2 as it could if there were no individuals of species 1 around. So how can we model this case? All right, this is the basic competition model. And when we actually write this model down, it's quite simple. Each species is using up carrying capacity for the other species. And this model is called Lotka-Volterra competition. Now, you've probably heard of Lotka-Volterra predation models. That's the kind of model like the lynx and the hare that end up producing kind of a oscillation growth pattern for both the predator and the prey. This is the Lotka-Volterra competition model, which is almost equally famous to the predation model, and it's the simplest way to model competition. So let's look at it a little more closely. You'll see a lot of similarities with the standard logistic growth model. The change in abundance for species 1 is equal to the R max for species 1 times the abundance of species 1 at time t times 1 minus, and if this was the basic logistic growth equation, it would be 1 minus N1 over K1. But instead, we modify it. We say 1 minus N1 plus alpha N2 divided by K1. And this alpha N2 term right here describes the degree to which individuals of species 2 are using up carrying capacity for species 1. So if there are some individuals of species 2 in here, it actually helps to fill up the carrying capacity. Remember, this is all the degree to which carrying capacity is empty, this is the degree to which carrying capacity is full, and species 2 is using up carrying capacity for species 1, right? In the same way, species 1 is using up carrying capacity for species 2. So in the species 2 equation, the change in abundance is equal to R times N2. This R could be species specific for N2, for species 2. And then we multiply that by this term, which in the absence of species 1 is just the same as the logistic growth model, 1 minus N2 over K2, but instead it's N2 plus beta times N1 over K2, all right? So this is, again, this beta N1 term is just representing the degree to which species 1 is filling up carrying capacity for species 2. All right, so the only difference between this and the basic logistic growth model is that the constants alpha and beta are included now in this model, and each one, alpha and beta, are measures of the effect of one species on the growth of the other species. These are competition coefficients, all right? And you can read more about this in the Gatelli book in chapter 5, all right? So a couple questions. Now, what does it mean if alpha is equal to 1? All right, so this is alpha term. So alpha is the degree to which individuals of species 2 use up the carrying capacity for species 1, right? So if alpha is 0, then this model just reduces to the standard logistic growth equation, and there is no competition because species 2 does not use up any carrying capacity for species 1. So there's no competition coefficient, no competition, all right? What if alpha is equal to 1? So if alpha is equal to 1, then species 1 and species 2 are indistinguishable in the degree to which they use up carrying capacity for species 1. Any individual of species 2 or species 1 both uses up carrying capacity equally, right? What if alpha is equal to 5? Well, that means that species 2 uses way more resources up than an individual of species 1, and therefore any individual of species 2 is kind of worth 5 times any individual of species 1 in terms of using up species 1's carrying capacity, right? What if alpha is equal to 1/5? Well, in that case, every individual of species 2 only uses up 1/5 the carrying capacity that an individual of species 1 uses up, all right? So you'd have to have 5 individuals of species 2 to use up carrying capacity to the same extent as one individual of species 1. And you can interpret the beta term exactly the same way. This is how you interpret these competition coefficients, all right? Hopefully that makes some sense. We can look at this model more in InsightMaker, which we will do next. Let's explore the Lotka-Volterra competition model in more detail in InsightMaker. Please click on where it says clone a basic non-interacting two-species model here. Just click on that link to open the InsightMaker model. It should look something like this. All right, I'll give you a second to get this model up and running. And before we make any modifications to this model, you might want to clone it first so you can make modifications to it. Otherwise, there's not much you can do with it. But let's, once you've got it up and running, let's just see what it looks like. It should look like logistic growth, right? Where both species, if you start them well under carrying capacity, this is carrying capacity for species 2, this is carrying capacity for species 1, and both species just exhibit the classic S-shaped logistic growth all the way up to carrying capacity. So this is just 2 logistic growth models that are independent. There is no competition, there's no predation, there's no interaction among these 2 species. So we are going to make the Lotka-Volterra competition model using this InsightMaker workspace. So we have a start, we have basic logistic growth, and we've seen how the Lotka-Volterra competition model is basically just a simple modification of the logistic growth model. So we remember there's just two parameters we have to add to make this a Lotka-Volterra competition model. We have to add an alpha term and a beta term. So I'm going to add two variables to this model, and I will call it alpha and beta. And I'll put alpha here, and I'll put beta here. Okay, so this is going to be alpha, which is the degree to which individuals of species 2 contribute to using up carrying capacity for species 1. And we have beta, which is the opposite, the degree to which individuals of species 1 use up carrying capacity for species 2. All right, and where do these link in? Well, in order for a competition to work, now alpha, remember, links into the equation for species 1 because it impacts the degree to which carrying capacity for species 1 is used up. So let's link alpha to species 1, and we'll link beta to species 2. All right, so far so good. What else do we need? Well, we need the actual interaction to occur. So in order for that to occur, we need species 2 to link to the growth of species 1. This is where species interaction can actually happen. So we need the abundance of species 2 to help define the growth for species 1. And it's going to be negative, right? Because it's competition. And this, likewise, species 1 influences the growth of species 2 in a negative way. So now we have the makings of a competition model. We just have to fill in the equation. So let's do that. Let's click on the equation editor for the flow for species 1. So again, species 1 is going to be growing exponentially times this this term, which indicates the degree to which carrying capacity is not used up. And instead of just allowing species 1 to use up its own carrying capacity, we have to add, and I'm going to add another parentheses here. And instead of just species 1, it's going to be species 1 plus alpha times species 2. So species 2 can now use up some of the carrying capacity for species 1. In just the same way, I can click on the equal sign for the flow for species 2, and I can see that species 2 growth is defined by this exponential term and then this density dependence term. And instead of just letting species 2 fill up the carrying capacity for species 2, we let species 1 fill up carrying capacity for species 2, but we have to multiply that by beta, the competition coefficient. All right, beta times species 1. And so now that's as simple as that. That we basically have the Lotka-Volterra competition model fully specified. We might want to add alpha and beta as value sliders so that we can play with different values. So let's add a value slider that goes from 0 to 5 for both alpha and beta. We'll just add it so that it goes from 0 to 5. And now we can play around with different values of competition coefficients. Now, if competition coefficients are 0, there is no competition, and it should be exactly the same as before. So let's just make sure, yep, everything looks good there. Now we can start playing around with different values of alpha and beta. And this is where the fun begins. One of the main questions that we ask in almost any species interaction model is about stability. Are the species able to coexist? Does one species outcompete the other? Can this system sustain both species? So let's look at that. I'll just pick some random alpha and beta values and run the model. Oh, one species that is outcompeting the other. In fact, species 2 is outcompeting species 1 in this case, right? So in this case, species 2 is a better competitor than species 1. At this point, I'm not going to go into great detail about why. We'll talk more about that in a few minutes, but what I'd like you to do is to play around with this system. So make sure you have a working competition model, and then go to the lecture webpage and let's start looking at some questions. What happens if one species is a superior competitor? What does it even mean to be a superior competitor? Can you identify some criteria that makes one species outcompete the other in terms of the alpha and beta, in terms of the carrying capacity of one species versus another? What does it mean to be a superior competitor? Can you identify a scenario where it's possible that both species coexist under this model? So try to find a scenario where both species are able to coexist, maybe at a level below their own carrying capacity, but still coexist, all right? And in fact, what I'd like you to do is to comment on Top Hat about the coexistence question. Again, this is one of the most fundamental questions of all species interaction models about coexistence. So play around with the model and see what you think. Can you identify some conditions that are necessary for coexistence in this simple Lotka-Volterra competition model? Next, I'd like you to think about, what if one species is an exotic invader? That is a potential invader of an ecosystem that's dominated by species 2. So species 1 is the invader, species 2 is already existing. And in fact, species 2 exists at its own carrying capacity. So the initial conditions has species 2 at its own carrying capacity and species 1 at very low abundance. It's just been introduced into the system. So just make it like 2 or something like that. Very low abundance for species 2, for species 1, and species 2 put at carrying capacity. Under what conditions is species 1 successful in invading this ecosystem? Can you identify a scenario where species 1 is successful in invading the system? And can you identify another scenario where species 1 is unsuccessful in invading the system? All right. And finally, think about stability and instability of equilibria that you might find. There are several equilibria that you probably identify relatively quickly. Are these equilibria stable or unstable? Remember, the way to look at stability or instability is to modify the initial abundances of species 1 or species 2 and see if it goes back to that equilibrium. Does it return to the equilibrium? That's a stable equilibrium. Or does it go to a different state? That's an unstable equilibrium. All right. So take a few minutes to play around with this Insight Maker model that represents a Lotka-Volterra competition model, and then we will come back and talk about some more math.